Swayam Prabha. Digital India. Educated India.
Welcome back to my course Aspects of Biochemical Engineering. I think in the last two lectures I tried to discuss both the momentum transfer and also mixing time in the bioreactors, and today this lecture I am going to discuss a very important topic, that is heat transfer. Now you can remember that in the previously I tried to discuss how you can explain this conduction, convection and radiation, because I have given the example that if you look at that one place, this here some kind of fire that has been created and we want to extinguish this fire, then there are three different approaches we have. Suppose there is a pond here, and in this pond I can, with the help of bucket, I can take the water, and one person can take the water and put the water in this for the fire extinguishing purpose. The another approach is that one person can take this bucket of water, give it to the one person standing here, one person standing here, one person standing here, and so he hand over the bucket here, he hand over the bucket here, he now hand over the bucket and here. So here what is happening, if you look at the first case, that both the water and the man is on our movement, but here that the water movement is there, but media is not moving because all the person they are standing here. Am I right? And another way we can do that, we can use some kind of pump, and we can spray this pump on the surface of this fire, so that the extinguishing of the fire take place. So three different mechanisms we have. Now this is we call is conduction. This was the person who is carrying the liquid and therefore just to subside the fire, and this is where the media is not liquid is going, but that media is not moving. That is we call convection, and this we call it radiation. So this is three mechanism, and which is largely apply in case of heat transfer. Let us see that heat transfer deals with the transport of different form of energy in the form of temperature. So this we understand. Now where so biochemical industry is largely applied, the reason is that we require the temperature control in case of a reactor, because I told you that organisms they require a particular temperature for their growth and metabolism. Then for sterilization, because sterilization is a very important part of fermentation industry, because we shall have to we kill the other organism that present in the system, so that our desired organism can grow, and insulation of the process 5 flow line. That also very much is required. Suppose we want to maintain, particularly in case of sterilizer, we have this pipe after the heat exchanger that should be totally insulated, so that we can maintain the temperature in the pipeline for the sterility of the liquid. So these are the now question comes that how you do the analysis of this heat transfer. First is the molecular. If you look at molecular heat transfer or conductive heat transfer, how you can express the heat flow through the material media without actual migration of the particle of the media region. That highly temperature is the lower temperature, high temperature to the low temperature. This how we can take place. Q equal to A into dA to the power dx. Am I right? Now, dA is the dt is the temperature difference, and dx is the thickness of that particular media, and A is the area that we have. So, we can write this is K is the proportionality constant. Now, Q is the heat transfer that I told you, heat transfer in the bath, and A is the area, x is the length of the conductive path, and dt by dx is the rate of change of temperature with distance measured in the direction of the heat flow, and K is the proportionality constant. Now, this is Q equal to this we can write. So, this we can write Q by A equal to Qx, you can write this form, and so Q equal to Qa into dx by dt. Now, this is initially you can remember we ask any kind of transfer is equal to driving force by resistance. So, we want to write this express the equation in that same form, that Q equal to del T by R, R is the resistance, and this resistance is nothing but del x A into K, that is the resistance. So, driving force is the temperature difference, and resistance is nothing but del x by A into K. Now, next is the convective heat transfer, and convection of the heat transfer by the mass motion of the fluid in such air or water, and convection among the hot surface occurred because of the hot air expands, and because let me give the example like this. It is the hot surface with the close at the bottom, you can see that here hot surface. So, it is going rise, and it will go rise, it will go rise and it will come back like this, it will go rise and come back like this. So, this is the cooler water descendants, and this is the warmer water rise. This is the phenomena, this is going on during the convection process. So, convection may be of two types. One is called natural convection or free convection, and another is forced convection, which is induced by the external means. Now, the natural convection, the flow induced by the different differences between the fluid density with the result due to temperature changes. Now, we understand that as we increase the temperature, the density is reduced, am I right? So, that results of temperature changes. The forces of forced convection externally induce flow with the such as wind. We use the kind of flow pattern, so that forced convection that take place. So, here the rate of heat transfer can be expressed like this, that Q equal to A into H into A del T, where H is the convective heat transfer coefficient, A is the heat transfer area, and del T is the temperature drop. Now, this is equal to, I can similarly we can, as we did in case of conduction, we can write in the same form driving force by resistance, and this will be 1 by AH. Now, Newton's law of cooling is that when the heat, that hot liquid temperature is TH and cool liquid TC, the natural convection heat flux equal to QA TH by TC. Now, the cell energy balance, the governing equation, we can explain like this: the rate of energy by molecular transport minus rate of energy by molecular energy out by molecular transport, rate of energy by convective transport, rate of energy out by convective transport, and rate of work done on the system, by the external force, and rate of energy production, all equal, that should be equal to 0. This is the governing equation. Now, this is the boundary conditions we have. The ambient temperature of the other surface may be specified at air temperature is given. Sometime heat flux normal to the surface is given. So, this has been given, I am not going through in details, you can easily find out. Heat of conduction form is spared. Now, before that we discuss about the in case of convection. Now, heat of conduction forms sphere of a stagnant fluid. This can be let us consider the heated sphere of radius r is suspended in a large motionless fluid, and hot sphere conducts heat to the surrounding fluid in the absence of convections. The following assumptions are maintained that steady state condition prevail, no convection heat flow in the fluid, the thermal conductivity K of the fluid is constant, heat flow only in the radial r direction, and heat flux at the surface can be evaluated by the individual law of cooling. So, this is how we can do that. This is the sphere, and this is the sphere, and this is the fluid that we have. This is the R, and this is the Tc, and this is the Tr is the difference. So, rate in the spherical surface R and rate R in the heat out at the spherical surface R plus R, that should be equal to 0, and which can be represented like this. This is the surface area, am I right? In the surface area of a sphere is 4 pi r square into keyword, this is R, and 4 pi r square into R plus del R. Now, this if you divide by 4 pi del R and del R tends to 0, we can write this equation in this form, and this we can integrating, we can write R square keyword equal to C1. C1 is a constant. Now, then by applying the Fourier's law of heat of conduction, we can write Q K dt by R, and then we can write dt by dr equal to Q R. This we can write this is in this form. We have seen before also. This we can write it here, and then our final equation will be getting this. This is equal to T equal to that C1 by Kr plus C2. Now, here the heat of combustion of spared to a stagnant fluid, the boundary condition T equal to Tr, where smaller is equal to capital R and T into Tc, and R tends to infinity, then your equation will be Tr equal to T by C1 by Kr plus C2, and Tc equal to C2, then we can write in this form C1 equal to Tr minus Tc K into R. Finally, we can write this equation that T equal to C1 into Kr and T1 minus Tc by Tr minus Tc equal to capital R by small r. Now, this is the combining resistance, because this is very important. This is when a system contains the several heat transfer resistance in series, overall resistance equal to sum of the individual resistance, and temperature changes across the entire structure. So, let us have this one resistance, two resistance, three resistance, and how the temperature changing like this, the different resistance that we have. So, total temperature change the del T across this layer, del 2 across this resistance, del 3 across this resistance. Now, the rate of heat conduction in the system under steady state condition governed by this equation. This is the driving force and this is the resistance, and resistance is the R1, R2, R3, and R1 can be expressed like this. We have shown you then V1 this is this like this. Now, individual and overall heat transfer coefficient, assume a simple case in which the hot fluid is flowing through a circular pipeline and cold fluid is flowing outside the pipeline. So, it is a kind of annular things, that we can write that this is like this. This is the hot liquid is flowing through a circular pipeline and cold liquid is outside the pipeline. So, here might be cold, and if you consider this heat, hot liquid. So, cold liquid and hot liquid, this is hot, am I right? So, the overall resistance of flow of the hot fluid to cold fluid is measured by three resistance. A resistance offered by the film of hot fluid, resistance offered by the metal wall, resistance offered by the film of the. So, you have three different layers. So, I have shown you this like this. So, here what he is saying that resistance offered by whole fluid, there will be, this is hot. So, this is, they have the resistance, then the wall has the resistance, and this is the cold fluid, the cold film, they have the resistance. Now, this is how we can explain like this. This is different layer that we have, and different resistance we can measure at different places. And this is 1, 2, 3 the different situation that we have, that this is different region that we have, that is the cold film, this is and this is the hot side, and this is the metal surface, metal wall is there. So, this is how this comes like this. So, the temperature is flowing like this and like this. So, you can write T1 to T2, T2 to T3, T2 to T4. Okay. So, here the heat transfer rate in the hot fluid can be expressed as Q into HI T1 by T2. Am I right? So, in case of wall, we can write what you can write, Q equal to A K into AW T2 minus T2 into XU. Then and AW is equal to what? AW is the surface area. Am I right? So, twice pi r is the surface area into length. So, you can cover all the surface area of the circular tube, and this is for sphere, we shall have to have the area is 4 pi r square. And in case of rate of heat for the cold fluid, we can write Q equal to H0 into H0 T2 minus T4. So, when we have the overall heat transfer, that you have the Q into U0 A0 T1 minus T4 T1 minus T4. Now, you combine all the equations, we will get in this form. Am I right? 1 by Ui AI equal to 1 by U0 A0 equal to this into this into this. This is the overall equation we will get. From that, we can derive this equation. You can see that equation, this one, and from this we can easily find out this equation. This is for thin tubes or cylinder, inside and outside radius are not much difference for the each other, and hence there is a combined equation will be right that. So, what we can see previously, that you see that previously this equation was our equation. Now, we consider this is same, is more or less they are not changing. Then what we can write? We can write this equation in this form. This is the form we can write. So, fouling factor, that is another important thing that we have in case of heat transfer. This is due to the continuous use of the heat surface equipment, dart and scale deposit on one or both sides of the pipe provided additional resistance to the heat flow and reduce the overall heat transfer coefficient. Now, I can take the example in the steam generator. And in case of steam generator, major problem is the scale formation in boiler tubes. What is happening now, if the scale formation there in the boiler tubes, then what will happen? The heat will not transfer properly, the conductivity of the metal that will be less, conductivity of the solid surface will be less. So, heat transfer, you require more heat, that is the fouling factor. Each fouling layer are associated with the heat transfer coefficient for scale, and dart coefficient is called fouling factors. So, this is if we consider that heat hot surface and cold surface, then we get the overall heat transfer equal to this is the we can write like this. The heat exchanger, the equipment involved in the heat exchanger is from hot liquid to cold or to cold fluid, either by conduction, convection or by radiation. Heat transfer equation can be divided as cooler, heater, condenser, etc. on the basis of its functionality. Some popular heat exchanger are double pipe heat exchanger. Because I work with this Citogia biochemical industry, we use the double pipe heat exchanger. Cell and tube heat exchanger mostly used in the different industry. Thin tube heat exchanger also used by the industry. Plate and frame heat exchanger largely used in the fermentation industries. So, their heat exchanger may be of different arrangement. One is parallel or co-current flow, counter current flow and cross flow. So, this is the kind of energy balance in the heat exchanger. This is the cold or hot cold. You can see this is the cold fluid in and the hot fluid out, and this is the heat exchanger, and cold fluid out and hot fluid in. That we have. So, here I can explain little bit. Suppose we have heat the plate heat exchanger. In case of plate heat exchanger, we can have like this. So, one plate we can pass the hot liquid and take out the hot liquid. Another plate we can pass the cold liquid and take out the cold liquid. That is like this. Now, this case 1, the steady state heat given out in the hot fluid is equal to the heat gained by the cold liquid. It can be expressed like this, that MC equal to like 8 C0 minus Ci, and similarly hot surface we can express. And so if you look at that, case 3 is the latent heat for the condenser surface of the coolant. It can be expressed at mH lambda and mCp CCO0 minus Ci equal to Q. mH is the rate of condensation of vapor, and lambda is the latent heat of condensation of vapor. Now, here the overall heat transfer can be expressed as like this: del U A del Tm, that is the mean temperature difference that we have. And mean temperature logarithm mean temperature difference is what? That is if the temperature varies, both fluid either counter current or co-current flow, the mean temperature difference will be logarithm mean of the differences. So, it will be d2 minus del t del 1 equal to ln del 2 by del 1. So, this is like this, we can express like this, and this logarithm average, this mean value is considered in case of calculations. And arithmetic mean of the temperature difference, that also can be calculated. In case of one fluid in the heat exchanger system remain as a constant temperature, such that the fermentation mean temperature difference is Tm, and will be arithmetically mean temperature difference. This will be Tf minus T2 T1 plus T2 divided by 2. This we can calculate like this, because in fermenter, suppose we want to maintain a particular temperature there, we can do that. Now, we have two problems that is related with this heat transfer. I hope if we can solve this problem, then our conception will be little bit clear. Now, what is saying that hot freshly sterile nutrient media is cooled in a double pipe heat exchanger before being used in the fermenter. Now, media leaving the sterilizer at the 121 degree centigrade, the exchanger flow, we know the sterilization temperature is 121 degree centigrade, that usual normal sterilization temperature, and flow rate is 10 cubic meter per hour. That desired outlet temperature is 30 degree centigrade, and heat from the media is raised to raise the temperature is 25 cubic meter per hour of water initially at. So, this chilled liquid is used to cool down the temperature to 30 degrees centigrade. And the system operated as a steady state. Assume that the nutrient media has the property of water. We assume the property of water remain unchanged with the change of temperature, and heat capacity of the water can be taken as 75.4 joule per gram per liter per gram mole per degree centigrade. Now, what will be the heat transfer what rate of heat transfer is required, and calculate the final temperature of cooling water as it leaves the heat exchanger. So, this is the problem that we shall have to solve. Let us see how we can solve it. Now, first we shall have to find out, as I told you, that we shall have to convert the unit to our desired unit. As for example, the hot liquid flow rate, that is 10 cubic meter per hour, that you have to convert into the second, the 2.78 kg per second. We can easily do that, because we know the density of water is 1000 kg per cubic meter. So, we can easily do that, and the similarly we can convert the flow rate of cool water, that is 6.994 kg per second, and the specific gravity of cool and hot water, that also we can convert it in this unit, the SI unit. Then we have the equation. What is the equation we have? Q equal to, we shall have to find out the rate of heat transfer. So, we have mH Cph Thi minus Tho. So, we can easily find out that how much is the heat that hot fluid, how much is the heat is given by the hot fluid, that you can calculate. Then for cool liquid, we can similarly find out the how much for the cool liquid is the temperature we have, and we assume the temperature of the cool liquid is this. Am I right? And if it is like this, then we can, from that we can find out that what is the cool liquid outlet temperature, that is we will be getting about 51.5 degrees centigrade. Therefore, the exit cooling water temperature will be 51.5 degrees centigrade. So, what basically we have done, we calculate from the hot liquid that how much heat actually coming out from the hot liquid, then that is transferred to the cold liquid, and from that cold liquid we can find out that what is the temperature of the outgoing temperature of the cold liquid that is have in the system, that will be coming, because the cold liquid is inlet temperature is 15 degrees centigrade, that is from the chiller, and this is the outgoing temperature of the cool liquid. So, this is very simple problem. And another problem that we have, like a fermenter used for antibiotics production must kept at 27 degrees centigrade. After considering the oxygen demand of the organism, the heat dissipated from the starter, and the maximum heat transfer rate required is estimated 550 kilowatt. Then cooling water is available at 10 degrees centigrade. The exit temperature of the cooling water is calculated using the heat balance at 25 degrees centigrade. Now, heat transfer coefficient of the fermentation broth is given, and heat transfer coefficient of the cooling water calculated as this, and it is proposed to install a helical cooling water coil inside the fermenter, and outside the diameter of the coil pipe is 8 centimeter, and pipe thickness is 5 millimeter, and thermal conductivity of the steel is 60 watt per meter per degree centigrade, and an average internal fouling factors of 88,500 watt per square meter per second is expected, and fermenter's side surface of the coil is kept relatively clean. What length of cooling coil is required. So, this is very interesting problem that we have, and we shall have to solve how this can be can be solved, and let us see how we can solve this. Now, as I mentioned that we shall have to always jot down what are the data is given, that heat transfer, that is already amount of heat transfer capacity is already given, this is 550 kilowatt, and temperature, respective temperature is also given, am I right? And that final temperature and all these things is given, and the thickness of the pipeline, that also given, and all you have to convert it into the SI unit. So, we converted into the SI unit everything, and then after converting into SI unit, then we find out the and HI and HIC also given in this problem. First we shall have to find out the arithmetic mean temperature difference, and because we want to maintain a particular temperature. So this is the final temperature is 27 degrees centigrade, and this is 10 to 25 by 2, we can easily find out, and HF fouling factor of the hot surface is neglected. Then this is the resistance that we have, 1 by U equal to this we can easily calculate, and we find out the U value. So, U value we can calculate, and this is the U value we can calculate. Then we know rate of heat transfer equal to U into A into this is temperature difference. So, if you put all this thing here, and we can easily find out the area that is required for the heat transfer, that heating pipeline. Now, we know that this is the surface area required for the heating purpose, and we know area is twice pi r into L. Twice pi r is the peripheral area and L is the length. So, this form that you can easily find out the length of the pipeline. So, in this particular lecture, I try to discuss the heat transfer, and heat transfer is very important aspects as per chemical and biochemical engineering is concerned. And we find that 3 type of heat transfer we have: conduction, convection and radiation. We try to find out how you can calculate the conductive heat transferred, how you can calculate the convective heat transferred. Then we try to solve 2 problems, and on the basis of that we can find out that what is the surface area required for cooling that heating surface, and also that what is the temperature required of the outgoing chilled water. Thank you very much.